how we define position, because how you define position determines how you define velocity, and how you define velocity defines how you define acceleration, and then how you calculate acceleration determines how you determine force, okay? So we're starting kind of this trifecta of things. Velocity, that's going to lead to acceleration. Acceleration is going to lead to force. So you have to have very solid groundwork upon which to build. So part of this is also terminology. And that's the difference between a scalar quantity and a vector quantity. So a scalar quantity only has magnitude, which is a fancy word for saying it's just a number, okay? So here's the classic example of a scalar quantity. One is mass, okay? So if this golf ball has a mass of 0.1 kilograms, it doesn't make any sense to give it a direction. It doesn't say, oh, it has a mass of 0.1 kilograms up or down or left or right, okay? It's just a mass, just a number, okay? Now, that's one example. Distance is another one. So if I said to Luke, I said, Luke, how far is it from your house to the school? Ballpark estimate. Mile, 2 miles, mile and a half?
Like 5.
5 miles. Okay? Now, if Luke just tells me that he lives 5 miles from the school, I just know that it's a number. I don't know in which direction that he lives. He might live 5 miles down below the house, the school, which would be really weird. Okay? Or yet, he might live 5 miles up above. I'm guessing he might live 5 miles east, north, south, something like that. Okay? But if he just says that he lives 5 miles away, that's just a number. Okay? I don't know which direction that he lives. I just know that he lives 5 miles away. That's it. Now, the other one is speed. Okay? So for those of you that drive over from May South, ballpark estimate. What's your average speed when you're driving from May South over here?
47.
47 miles per hour. Okay? Now, I don't know which direction Miss Dozer is driving. Okay? I don't know if she's going up Tyler and coming across. I don't know if she's going over Maze Road, coming up 119. I don't know. If she just says, hey, I'm driving 47 miles per hour, that's just a number. Okay, that's it. So your speedometer is called a speedometer because it just tells you how fast you're going. It's just a number. Now, I don't want you to look at scalar quantities and go, oh, those are the lesser of the quantities. Okay, it's like they only have magnitude. Don't get judgy with them. Okay, don't. Okay, it's just the hand that they're dealt. And sometimes we don't need direction. Energy, one of the most important things that we're going to talk about in this class. Energy is a scalar quantity. Energy doesn't have a direction, okay? It's just energy, right? So don't look at this and go, oh man, scalar quantities, okay? Don't get judgy about the scalar quantities, okay? Now, vector quantities have a number, but they also have a direction, which means we can represent them as an arrow. Now, if Miss Dozer says, I drive 47 miles per hour north when I leave May South, that now becomes a vector quantity. Because now it's like, oh, she's telling me which direction that she's going. She's going to turn left and then she's going to go west on 45th Street. Again, that now becomes a vector quantity. If I ask Luke, which direction do you live from the school? South, north, east, west, up, down? South. Now, if Luke says, I live 5 miles per hour or 5 miles south, the vector quantity equivalent of that, you can have velocity, and something called displacement, okay? So displacement is a distance with a direction. So as soon as Luke says, hey, I live 5 miles south, that becomes a vector quantity. Because then I can say, here's the school, Luke lives 5 miles in that direction. I can draw it with an arrow. But if he just says, I live 5 miles away, it's great. I know how far away he lives. I don't know which direction that he lives. But if he says, I live 5 miles south, then it becomes a vector quantity. So the most common ones we're going to use in terms of vector quantities are displacement, velocity, and acceleration. Okay? Eventually we'll get into forces, which are also vector quantities. But the first big three we're going to deal with are displacement, velocity, and acceleration. Now, displacement has a very, very specific mathematical way to calculate this. So technically, displacement, usually shown by like x, sometimes you'll see it shown as d, is position final minus position initial. Okay? And that's some very specific terms of this. But here's the problem. Even before you define position, you have to talk about what we call a frame of reference and a reference point. Okay? So, Mr. Hanna, how would you describe your position in this room? If someone says, hey, where do you sit in Burkamp's room? What would you say?
The closest chair to the door.
Which door?
The front door. Yeah.
Okay? Close, you're close to the front. How far away? In meters.
Meters.
Yes. Ballpark.
About 2.
2 meters.
Yeah.
Up, down, left, right, north, south, east, west.
Oh, wait.
You could be 2 meters above the door.
Oh, 2 meters to the right.
Your right or my right?
My right.
Okay? Because you're 2 meters to my left.
Whoa.
How about north?
North.
Oh, I like that.
I don't know directions.
Okay. North, south, west, east. Okay.
Not good to it.
Now, here's the story. What Mr. Hanna did, without knowing it, is that he chose the front door, an odd combination, he chose the front door as his reference point. He defined his position relative to the front door. Okay? He could have picked any point in this room. He could have picked the F equals MA sign. He could have picked the water jug over there. Okay? He could have picked the stapler. He could have picked the other door in the back. Okay? He happened to pick that front door. There's nothing magic about that front door. It isn't like, oh, that's magical. Okay? It's the door. Okay? He could have picked any point within this room to say, here's how I'm going to define my position. Okay? Now, when we start talking about velocity and movement, initially, we're not going to be allowed to move in circles. We will eventually. Okay? So, if I'm going to talk about velocity, which is going to be a change in this position. So Mr. Hanna gets up and he goes, hey, Luke's on fire, I'm going to go get the fire extinguisher, which would be bad. Okay? But at least he's going to try and put him out. So he's going to go get the fire extinguisher. So he's going to have a change in his position. Okay? Now, when you calculate that displacement, and we'll see this in just a second, that's going to be P minus P naught, his final minus his initial. So imagine that he can only walk towards the fire extinguisher and back. He cannot go all the way around by the sink and the water tank and all the way around and come around this way. He can only go back and forth along the plane. Now, here's what I want to do. So, imagine this is like one big number line. And we're going to make this point the reference point, and we're going to call this 0. So, the banjo, pardon me, stunned. So, a little bit out of tune. So, the banjo is going to tell me which direction that I'm going to go. So, here's the reference point. We can have 1 meter, 2 meter, 3 meters. Do you want these positions over here to be positive or negative numbers?
Negative.
Negative, okay. So this would be -1, -2, -3. Which means this side over here would be +1, +2, +3. There's nothing magic about this. You could have made those numbers positive and you could have made those numbers negative. Okay? It's arbitrary. It's your system, however you want to define it. But you all said, hey, I want those numbers to be negative. Cool. Okay. So, I'm going to move in this direction. I'm going to start at the reference point, and I'm going to go over here to, I'm going to point in this direction because this is the direction I'm going to go, and I'm going to come over here, and I'm going to end up at -3. Okay? So I went from 0 to -3. I moved. Had a displacement. So, here's the difference between distance and displacement. Conrad, what distance did I move?
3 meters.
Because distance is just a number, okay? So if he just says, hey, Burkamp, you moved 3 meters. I don't know which direction that I went. Maybe I jumped up 3 meters. Maybe I dug a hole 3 meters deep. Maybe I went there. He just says, hey, I went 3 meters, okay? I don't know which direction that I went. I just know I went 3 meters. Because that's just a number. Now, if we calculate displacement, and this is why this is a very technical mathematical definition, but displacement has to be right because if displacement is wrong, velocity is wrong. If velocity is wrong, acceleration is wrong. If acceleration is wrong, force is wrong. That's why you have to lay a very solid definition of how this is going to play out. So, here's the story. So here's this big number line. Here's the reference point. And I gotta do this backwards from what you guys are looking at. Okay, you guys are looking on that side. So that's -1, -2, -3. Okay? +1, +2. Okay, I have to think because like what I write is the reverse of what you all see in terms of which side is which. Okay, so I started here and then I went over here to -3. Okay? So Chloe, what was my initial position? 0. So P naught is going to be 0 meters. So what's my final position, Chloe? -3 meters. So what's my displacement?
3.
3 or -3?
-3.
Why? There's a big difference between the two.
Because you went towards the negatives.
Yes. Or, mathematically, if you look at displacement being position final minus position initial. Oh, I'm going to take -3 meters minus 0. I'm going to get -3 meters. Okay? So that's my displacement. Now, as soon as I can put a negative sign on there, now this says, oh man, this is now a vector quantity. Because I can draw that arrow that shows two things. How far I went to -3, and the direction that I went. Shows two things, my magnitude and my direction. Okay, cool as that. Whoa. Now, I went over here, pause for dramatic effect, and now I'm going to come back over here. Okay? So Dylan, on the return trip, what is, I hate my pen today. On the return trip, what's my initial position?
Your initial position should be
You're making this difficult.
should be 0, right?
No, on the return trip, where did I start?
Start away over there at -3.
I started at -3. So on the return trip, my initial position is going to be -3 meters. What's my final position?
0.
0. So my final position is going to be 0. Now, Deacon, what's my displacement going to be?
3 meters.
Why?
Because you're moving 3 meters in the positive direction. Back.
I like more of a math answer. Speak to my inner math nerd. You don't have to yell. I got a pretty strong inner math nerd.
your, 0 minus -3.
Ah, there you go, right? How do you calculate displacement? Ah. Your displacement is going to be position final minus position initial. So my final position is 0 minus a -3 meters. I'm going to get 3 meters. Again, that now has a magnitude and it has a direction. Oh, I came back in this direction. Okay? It's a vector quantity, right? Magnitude and direction. It's cool, right? Now, Connor A, what's my distance on my return trip?
3 meters.
So here's the story. Distance is 3 meters out, 3 meters back. That's just a scalar quantity. 3 meters. 3 and 3. But if I talk about displacement, oh, right, now I'm talking about vector quantities. My displacement is going to be -3 going out, +3 coming back. Okay? Now, here's the importance of how you define your reference point. Let's say I take this ball and I throw it up in the air, bounce back down. There's 2 options that you can have as the reference point. You can let my hand be the reference point, or you can let the ceiling be the reference point. Mac, if my hand is the reference point, how would you describe the motion in terms of where it is relative to my hand?
Above,
And then it's going to
go down.
come back down. So if my hand is the reference point, you would say it goes away from my hand and then it returns back. Okay? That's one description, if my hand is the reference point. Mac, what if the ceiling is the reference point?
It's going down and then up.
So you would say it goes towards it and then away from it, right? So if my hand is the reference point, it goes away and comes back. If the ceiling is the reference point, it goes towards it and then it goes away. It's completely arbitrary. When I set up this system, I could have made that side positive and that side negative. Doesn't make any difference. If you want up to be positive, great. If you want up to be negative, that's great. Okay? It's however you define the system. But typically, things going up are defined as positive, things going to the right are positive. Things going down are negative, things going to the left are negative. Typically, that's kind of a standard way to view things. Now, let's look at the difference between speed and velocity. Okay? So, being the age that I am, so I'm going to stroll over here. I'm big into strolling at this point in my life. And you got a stopwatch. Mitchell has a stopwatch, and he times it. It's like, Burkamp, I can use an hourglass to watch you move this fast. Okay? So he times me, right? And it takes 3 seconds. It's like, wow, that took forever for you to get over it. Okay, go. So, if I'm going to look at speed, and here's the difference. Speed is distance divided by time. So, Connor A, correctly said that the distance that I traveled was 3 meters, and it took 3 seconds, so my speed going out was 1 meter per second. Is my speed coming back, assuming that it took me 3 seconds, also 1 meter per second? Yeah. So my speed going out, my speed coming back, both 1 meter per second. Okay? That's a vector, that's a scalar quantity. I don't know which direction that I'm going. I'm just happy to be moving at this point. Okay? I'm moving. Cool. I don't know which way. I'm just moving. Now, velocity. Let's chit-chat about velocity. So, if speed is distance divided by time, how do you think we're going to calculate velocity? What'd you say?
I'm not
It rhymes with displacement.
displacement.
Displacement divided by time. Now, here's the difference. On the way out, my displacement was -3 meters. The time was 3 seconds. That was -1 meter per second. Okay? -1. That's now a vector quantity, because now that's going to tell me that I went in that direction. Okay, and we define that as being negative. So the banjo was pointing in this direction. Okay, I was coming over here, I had a nice leisurely stroll, I'm here. Now, at this point, I'm gonna go back. What's the banjo gonna do? Banjo's gonna flip around, okay? Now it's gonna go like this, okay? So as soon as the banjo flips around, I change direction, right? Now, something magic is gonna happen. Not necessarily magic, but somewhat. So here's the story. On the return trip, I'm gonna take 3 meters and divide that by 3 seconds, and now I'm gonna get positive 1 meter per second. Cool. Now, did I change direction?
Yeah.
Yes. What happened to the sign of velocity? Did it change sign?
Yes.
Because it went from negative 2?
Positive.
Now, human beings are very, 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 very good at seeing patterns. Okay, our brains are wired that way. Here's the pattern that I do not want you to see. I don't want you to look at this and go, oh, negative velocity means that I go away from the reference point, and positive velocity means that I come back towards the reference point. No, get that out of your minds right now. Stop. Do not think that. Okay? And here's the reason why. I had positive velocity, and I was going this way. If I happen to keep going past the reference point like this, I went past the reference point. Did my velocity change sign?
No.
Why? In
Because
terms of the banjo.
the banjo passed the reference point, and let's just say that the reference point.
You're making this so complicated. Did the banjo change direction?
No.
It still pointed this way. As long as the banjo is pointing this way, my velocity is going to be positive. If the banjo points that way, it's negative. Where I am relative to the reference point has no bearing on the story. Okay? All I know is that either it's going that way or it's going that way. That's the only option that I got. Cool with this. Okay. Now, are you leaving us?
Yeah, I got an appointment at 1:30.
Okay, here.
I get that.
There you go. That's a computer simulation, Phet Man. You can do a search, follow the instructions, that's all you got. Yep, that's the tomorrow. Okay, if you want, I can send you the link to the rest of the YouTube video.
Yeah.
I'll make that happen. See you, Connor. Man,
Alright, thanks.
and I'm 1 Connor down. Lost a third of my Connors. Okay,
But then again,
I can handle it. I can work with you. Okay. So here's what I do want you to see. And this is going to be an absolute truth. Did I change direction when I got over there and came back?
yeah.
Did my velocity change sign?
Yeah.
Yes. So here's one of the absolute golden rules, universal, no exceptions. If you change direction, and again, I'm not talking circles. This is not circles. Do not talk, oh, but I can move around. No. This is movement along a plane. If your direction changes sign, your velocity changes, if your direction changes, your velocity changes sign. So if I take this ball and I throw it up in the air, did it change direction?
Yeah.
Absolutely it did. So if you define up as being positive, it's going to have positive velocity on the way up. It's going to have negative velocity on the way down. Okay? If you define up as being negative, which you could, you would have negative velocity on the way up and you would have positive velocity on the way down. So what you see is we're going to look at some very complex motion. But if you keep certain rules in mind, they become very simple. Okay? So situations that look complex can become very simple if you break them down. Oh, hey, I throw this up in the air. Right. Change its direction. I know at some point my velocity has to change sign. Now, that's rule number 1. Now, rule number 2. So, let's say that you're driving to school in your carrot car, and you realize that you have left your Scooby-Doo lunch pail at home. I was like, oh, This is bad. Pain, suffering, agony.
Oh, going.
Pain, suffering, agony.
Suffering.
Hello. How are you? I'm good. How's that son of yours? Fantastic. He has left the building. All right, thank you. Bye. Random phone call. I didn't know who the person was. I thought I'd ask about your son. Weird. Okay. No, actually, I knew the person. What did you ask about their son? You didn't know? No, I did. All right. So here's the story. So, who was I talking about? Who left their Scooby-Doo lunch pail?
Jimmy.
Huh?
I don't think you said it.
Why not use probably on Jimmy? It's one of those templates pretty
Okay.
good.
Charles.
Charles.
Just sit Charles.
Charles.
Come on, man.
Charles is driving along, and he realizes that he has forgot his Scooby-Doo lunch pail at home. And if he doesn't have the Scooby-Doo lunch pail, bad things are going to happen. So he's got to change direction, right? So now he can't drive around in a circle. So the only thing he can do is kind of like what the golf ball does. It can go up, come back down. So you're driving away from the Scooby-Doo lunch pail, and you want to go back and get it. So what are you going to do?
Go back.
How? Talk me through this. You're driving, right?
Yeah.
You want to go back and get your Scooby-Doo lunch pail.
Turn around.
How? What are you going to do? Let me give you a hint. Are you going to hit the gas pedal or the brake?
Great.
Why?
Because I don't want to keep going that direction.
You want to slow down, right? Okay? So, when you talk about motion, we can represent them with velocity vectors. So here's your initial, here's V1 when you, this is V1. At this point, you're going, man, I forgot my Scooby-Doo lunch pail. You're going to hit the brakes, right?
Yep.
When you hit the brakes, what's going to happen to your velocity vectors? Now, here's the beauty. This first test, which is looking like it's going to be the Friday before Labor Day weekend, is going to be on acceleration. The beauty of acceleration is that you only have one of two options with acceleration. Either you speed up or you slow down. That's it. Okay, literally. Every acceleration problem that I type only can play out one of two ways. Either Charles speeds up, Charles slows down. That's it. It is. It's from the perspective of options, it's boring. Do I make it speed up? Do I make it? That's it. It's a two-trick pony. Speed up, slow down. So here's your V1. So only one of two things could happen on this acceleration. Either the velocity vector is going to get bigger and he's going to speed up, or the velocity vector is going to get smaller and you're going to slow down. What's going to happen?
Slow down.
You're going to slow down. So you're going to go, oh, there's V2, there's V3. Now, at some point you slow down enough, you're going to stop, right? Then what are you going to do?
Go back the other way.
What are you going to press? Gas
The
pedal or
gas.
brake? Oh, now, and you press the gas pedal to speed up, right? So then, if you're defining this direction as being positive, then he would have negative V1, negative V2, negative V3. Now, notice here your velocity vectors are getting
Bigger.
bigger. Literally, every acceleration problem is only one of two things. Either your velocity vectors get bigger and you speed up, or your velocity vectors get smaller and you slow down. That's it. Okay? That's it. Those are the only options. That's it. There's nothing else. Okay? Eventually, I will make you accelerate and move in circles, but not on the first test. We'll deal with that later. So here's the story. If you look at the sequence, Charles, you had to do three things to change direction. What three things did you do to change direction?
Slow down.
You had to slow down,
Stop.
you had to stop, and then you
Accelerate. Or speed up.
sped up, right? Speeds up, however you want, whichever verb tense that you want to use. Okay? So if you're going to change direction, these three things have to happen in this sequence. Okay? You can't get them out of the sequence Charles can't go, oh, hey, right, hey man, I forgot my Scooby-Doo lunch pail. I'm going to press down on the gas pedal. I'm going to go faster. No, he's not going to be able to turn around. And he can't stop until he slows down. I take this ball and I throw it up in the air. Did it change direction?
Yes.
Did that ball going up in the air satisfy these three conditions?
Yes. Yes.
What did it do, Mr. Hanna?
It sped up, it stopped.
No. On the way up, what did it do? On the way up, was it speeding up or slowing down?
It was slowing down
So on the way up, it was slowing down. When do you think it stopped?
at its peak.
At its apex.
Yeah.
And then on the way down, what did it start to do?
It started to speed up.
Began to speed up. That's it. Okay? You do this. Same thing. Now, if I drop it, hits the floor, or the table in this case. When it hits the floor, did it change direction? Yes.
Yes.
What did it have to do?
Slow down.
Slow down. Stop.
Speed up.
Speed back up. Now here's the difference. If I throw it up in the air, that process takes a while, right? Oh, it's slowing down, and then it's going to speed back up. Okay? But when it hits the table, that happens very rapidly. Okay? But it's still going to be the exact same thing. So when it comes in contact with the ground, it very, very rapidly slows down and stores energy in the compression of the golf ball. It stops, and then that golf ball expands, and it makes it speed back up. So anytime you see something changing direction, three things have to happen. Slow down, stop, speed back up. No exceptions, none, zero zip. It isn't like I'm going to come in tomorrow and go, hey, there's an exception to that. No, there's not. Okay, there's not. Now, here's the next thing. So let's look at that ball on the way up. Okay? So I'm going to give it some V1. Alex, do you want up to be positive or negative?
Positive.
Okay, so it's going to start with some positive velocity. He could have picked negative, he chose positive. Now, this is going to be as soon as it leaves my hand. As soon as it leaves my hand, what does it begin to do?
Begins to
Slow down. Begins to slow down. So now, I'm going to draw V2 a little bit smaller, and I'm going to draw V3 even smaller. Again, here's the beauty of acceleration problems. You can only do one of two things. You can either speed up or you can slow down, and that's it. So if I draw that as V1, the only thing that can happen is either that velocity vector gets bigger or that velocity vector gets smaller. That's it. No other thing in town. Oh, it's slowing down on the way up. I'm going to make them get smaller. Now, on the way up, listen to me very carefully. Deacon, on the way up, is the ball accelerating?
Yes.
Now, which direction do you think the acceleration vectors are going to point? Up or down?
Up.
Why?
Because it's slowing down.
Slowing down. So, you have positive velocity on the way up. So your acceleration vectors tell you, listen to me very carefully, your acceleration vectors point in the direction that the velocity vectors are changing. Okay? So the velocity vectors are pointing up, but they're getting smaller. Okay? So on the way up, I'm going to have an acceleration vector that's going to be a negative value. Okay? I'm going to have negative acceleration on the way up. Okay? Now, because I have positive velocity and it's slowing down, so my acceleration vector is going to point in the opposite direction. Now, on the way down, Charles, which direction are my velocity vectors going to point?
Down.
Down. Are they going to get bigger or smaller?
Bigger.
Bigger. So there's negative V1. There's negative V2. There's negative V3. Is it accelerating on the way down? Yes, because the velocity vectors are getting.
Bigger.
Now, which direction are my acceleration vectors going to point? Deacon, which direction are my acceleration vectors going to point, up or down?
Down.
Down. You said that with no confidence. Now, here's the story. This negative acceleration vector made it slow down. That negative acceleration vector made it. Oh, look what happens. You have positive velocity and you have negative acceleration. They have opposite signs. Velocity and acceleration have opposite signs. Is it speeding up or slowing down? Slowing down. On the way down, you have negative velocity and you have negative acceleration. What are you doing?
Just speeding up.
Speeding up. So here's the other absolute golden rule. Again, acceleration. Your only two options are what? Speeding up or slowing down. That's it. So if you're speeding up, your velocity and your acceleration vectors have the same sign. If you're slowing down, they have.
The opposite side.
That's it. There is no exceptions to the rule. So when you read a problem, hey, Charles is driving his car and he's slowing down. Right away, you know velocity and acceleration have to have opposite signs. Okay? If I say, hey, Mac is driving the car and Mac is speeding up, right away, the velocity and acceleration have to have the same sign. Now, here's what I want you to get out of your minds right now. That negative acceleration always means that you slow down.
No.
You can speed up with negative acceleration, but you have to have negative velocity. Could you speed up with positive acceleration?
Yes.
But your velocity would have to be.
Positive.
Could you slow down with positive acceleration?
Yes.
Yes.
But you'd have to have negative acceleration. Okay. Got the idea? Got it? Good, Grant? Okay. So, here we go. What is it? Just keep going. Forget it. I don't have much more to say.
Which I run.
Huh?
Which I run because this person called it.
Okay. So this is one of the very few times I use technology, because generally technology and I don't get along. So what you want to do is do a search for, and this is, I've got it up there in the front of the lab. It's called the Phet Simulation Moving Man. Okay? I'm sure you might have worked with Phet simulations before in some of your previous classes. Okay? It's a cool deal. So when you get there, you're going to have an option. You want to run the, it'll be whatever the top option is, okay? You don't want to download it because your computer won't allow you to download it. So just get on, find this program. So here's what you're going to do. You're basically going to use this, what I call the dude, okay? Literally, when you read the instructions, he's just the dude. And you're going to look at different scenarios. So the cool part about this program is that you can look at different graphs. We're going to look at 3 different types of graphs. Position time, velocity time, and acceleration time, okay? They all have time on the x-axis. Position keeps track of where you are. Notice that it's not distance versus time, it's position versus time. It's where you are relative to the reference point, and they're defining the reference point of being 0 right in the middle. Numbers to the right are positive, numbers to the left are negative. You can plug in different values of velocity, you can plug in different values of acceleration. If you're a graphical kind of person, you can tell them to show the vectors. So, you're going to go through this, and I'm going to lay out some different parameters. So, you can alter the acceleration, you can alter the velocity. You can just grab the dude and move him across the screen like that, okay? Or you can set the values and then make him move. So, I'm done. So basically this is going to be, hey, what do these graphs look like? Some of them are going to be horizontal lines, some of them are going to be straight sloping lines. Now, here's the story. let's talk about the velocity time graph. You're gonna eventually make the dude change direction. If the dude is gonna change direction, what three things have to happen? Slow down, be back up. So on your velocity time graph, what will happen if the dude changes direction? Here is 0 meters per second. Freshmen cannot go slower than 0. If you're in 0, you have stopped. So if you're going to change direction on a velocity time graph, that has to cross through 0, 0, because you've got to approach 0 meters per second. You're going to hit 0, and then you're going to speed up, because then you're going to be going away from negative. So anytime you change direction, your velocity time graph has to cross through that 0 meter per second line. Okay, I'm done. You're on your own. You have the rest of the time to work on that.